So for those who don't know me, I'm Manuel. I'm a postdoc here at Kent. And this is the first, as Julian pointed out, first workshop on AOG things. I don't know how you want to call it, Julian. So I took the liberty to organize one on showing how to create a 3D model with the intention of printing it using our 3D printer, because I felt that this is a skill that is very, very useful for all of us, because we are all building optic setups, and sometimes we just need a custom bracket to hold a lens and maybe a non-custom distance, or it's quite a small constraint thing, and the brackets you buy from Thor Labs might not be flexible enough for that application. So because on that note, I felt, I've done that many times, and it is useful. So I sent a plan ahead of time. I'm not sure if people looked at it, but the idea is I'll start by presenting a little bit on the different kinds of 3D printing, and really the one we are going to be using and thinking about is FDM, fusion deposition modeling, because that is the printer that we've got here in the lab. And I've got now here the page of the manufacturer, the Sla. And effectively, this is our printer. It's a smallish benchtop, relatively inexpensive. I think Mike and Adrian B paid less than £400 for it, all in all. And the way FDM works is you've got a roll of filament, which it's a form of plastic, which actually in this printer is actually kept on the right-hand side. There's an enclosed area. And you've got an extruder that heats up the filament to 210 degrees. I think for PLA, that is the melting point. And as it moves the heads around the build area, it deposits filament in specific locations. So the filament is on, off, so repeatedly bringing the filament above and below the melting point. So that's how you can control the deposition of filament in place. And because you have control over the X, Y, Z, you can build a model effectively. So that is how FDM works. So it's, a lot of, it's by far, I would say, the most common method of 3D printing, and the more accessible, cheaper printers in the market, they all do FDM. And printing in PLA, polylactic acid, I believe that's how it's called, which is a form of plastic that is actually made out of sugarcane, from what I remember. So it's quite non-toxic, and it's very recyclable, precisely because it's very, I think it's compostable. Don't quote me on that. This printer allows also to print in ABS plastic, which is a more resilient plastic, but ABS has all sorts of other problems, because when you heat the plastic, you release vapors. And for ABS, at least, those vapors can be carcinogenic, so you need a proper extraction system. So we don't actually print anything in ABS in this printer. We only print in PLA. So that is effectively in a nutshell, the 3D printer and like the 5-minute elevator pitch. One thing that we have to bear in mind with PLA is the filament absorbs water. So when we open a roll of filament, it's got a certain shelf life of a couple of months, depending on how humid the room is and how warm. We have to bear that in mind. So this printer only has one extruder, so it only prints in one color, if you want to call it that, because you can buy the filaments of multiple colors as well. So yeah, this image here is a bit misleading, because you can't actually obtain a polychromatic model like that unless you change the filament halfway through. You can always paint it. And there are things that we can do. There are chemicals you can use to treat and smooth out the the PLA filament, and then prepare them for being painted. But I would say for 99.9% of the usage cases here, you will not bother with that. You just print in whatever color you've got, and you put it in your system. So yeah. So these are some of the things that the printer has. So this is quite nice because it's enclosed, because it's kept in our workshop, our prep room, and that can be a little bit dusty. So the whole build area is enclosed. It's got a lid. You've seen the printer before. The print volume, this is how large the model can be. So it's, in this case, it's 15 by 15 by 15 centimeters. So if you want something bigger, you will need to either print it in, think about how you can print it in multiple bits and then add the bits together, or speak to someone on campus. There's the School of Computing has a big, George, can I mute you?
Oh, excuse me.
You seem to have a lot of background noise from you.
I'm still eating. I'm so sorry.
That's all right, no worries. Okay. Okay, so as I was saying, the university has, the School of Computing has a maker space, and now the engineering school also has a maker space. And so you can actually get them to print bigger things, and perhaps with better resolution, which is something I was actually puts me nicely into the next step, which is to talk about resolution and whatnot. So FDM has limitations in terms of resolution. It's not just about the precision limits of the stages, the three motorized stages that the system has. It's also about the fact that because it's depositing, if you slow down the process, you actually have larger drops. What I'm trying to say here is that you cannot just look at the minimum translation step from the stages and think, okay, this is the feature size, the resolution of this printer, because it's not. So there are other methods to print smaller things, and one of them is SLA, stereo lithography. So this method is completely different, because it actually doesn't involve depositing a filament. It uses a resin and a laser that UV cures, or a UV laser that cures parts of the filament, and that's why it's stereo in this case, because you effectively project or illuminate specific areas of the volume of resin, and they get cured, and others in the neighboring area do not. And so because of that, you can then afterwards wash the rest of the resin and are left with some solid bits. And because you are using effectively an optical system, the resolution is actually better. But I cannot really go, and I don't really want to go into too much detail here. Firstly, because we don't have such printer, and secondly, because it's not something I've actually researched that much, because precisely we don't have one. So we are going to focus on this printer, and I'm going to show you later how you can load things into this printer, but I just wanted to give you a brief 5-minute introduction to how these printers work and what are their limitations. And one of the obvious limitations is when you build something to put in your system, chances are you might need to bolt it somewhere, or you might have components that you want to immobilize inside of the 3D printed component, which means you probably will want to put a set screw at some point and put threads. And that is a problem, down to the limited resolution, and also down to the material itself being quite brittle. Threads are kind of the Achilles heel of these printers. So actually, a more clever idea than doing an actual, trying to model a thread in the 3D printing, the 3D modeling software, and then getting the printer to print it, is to actually do what we call a nut capture. A nut capture effectively is, as the name implies, a structure to capture a nut. So a hexagonal nut that you use in the lab. You've got lots of them lying about in your labs. You create a hex-shaped hole, and you've got the dimensions for them. And after you've printed the part, you simply drop the hex nut in there, and that forms the thread, if you want to call it that. Now, it's important that we always put the threads. Maybe I should set my trusty. Oh, this doesn't work because I am. Oh, it does. Okay. So what I'm saying is, so if we have. Sorry, I'm just drawing something here. So if we have, this is the outside. So this is the okay, this doesn't work. Stop sharing the camera. So you've got here the outside of the part, and we built a nut capture here. This is not going to work because if we want to screw it in, the motion of putting the screw in is going to pull the nut out. So we actually want to insert the nut capture down here, and then the screw can come from the outside, but then the nut will press against the inside of the structure. Does that make sense? And another little nifty trick that I learned recently is you can make the nut capture slightly, but ever so slightly narrower than the nut itself. Then what you do, grab the soldering iron, and you use the soldering iron to touch the nut, heat it up, and because the melting point of PLA is only 210 degrees, the soldering iron will be on 300, 400 degrees easily. Well, probably not 400, but it will be higher than 210. So you heat up the nut, and the nut will effectively melt the surroundings and lock itself in, so quite neatly. So that's quite a good thing to do. Strength of the material, that is an important thing. So obviously, anything that is extremely load bearing, I think that goes without saying, you shouldn't do 3D prints on. I mean, most of our components are relatively lightweight, or lenses, collimators, etc. So that is not really a problem. But if you do it, if you do the model properly, you can actually have a little bit of strength. So I give an example. I've got a handheld probe in one of my OCT systems, and the handle for it was 3D printed. And I think Ramona, I don't know if Ramona is in the meeting, but she had a similar one as well printed for her. And as long as it's thick and designed properly, you can have a little bit of load. But again, your mileage may vary. Obviously, you wouldn't want to have something that it's critical and supporting a lot of weight being 3D printed. That's, again, something to bear in mind. So I guess I've already spoke about feature size. I already spoke a little bit about temperature. So obviously, if you're going to use this in a highly hot environment, and highly hot, by highly hot, I mean in the vicinity of 200 degrees, PLA is probably not the best thing for you. But again, I don't think you would be using it in that kind of environment here anyway. So I've got here, but perhaps the issue with supports, I will explain those when we actually slice the software, use the slicing software. Right. So moving swiftly on, because I know Adrian B has to get away. The first step is obviously building your model. And so you need to make sure that you've taken the necessary measurements. I think I've got here a little thing. So, and take the necessary measurements, do a sketch. So before what I always do is before I go in Fusion, I simply draw what I want to do. I just do a sketch. I think that's the same with everyone. So I know roughly what I want. So in this case, what I'm doing is I am building a little bracket which will house a collimator, one of those F-series 4 labs collimators, FCAPC, and a cylindrical lens mounted in front of it. So actually, this is more or less what I'm going to have to do for myself in my lab. So I'm using this as an example, and effectively I need to fix this to a translation stage. So these all brackets. So I have to put 2 holes in here, put screws through. Those will lock onto the top of the translation stage, and this is effectively what I want. I want to be able to put the collimator in here and have a cylindrical lens centered and at a specific distance from the collimator, right? So you start with a sketch, then you go in the lab and you measure the actual distances. So this is a top view of the same bracket, and now I know, okay, I need the space between these 2 holes is 150. You make a note. Actually, I didn't make it here, but of the diameter, what kind of screws you need to make sure you've got enough clearance to get them through. What is the diameter of the collimator, and what is the focal length, or the distances between the collimator and the cylindrical lens. Not that critical because this beam is going to be collimated anyway. But and all of that. So you do all of these bits, and now you're ready to actually take this and open a software to create your 3D model. So if you looked in the notes that I've circulated ahead of these, there were a number of different softwares that I suggested. There was a big list. You've got lots, you know, the sky's the limit. There are some free ones, there are some commercial ones, there are some that have completely different paradigms. So the one on the bottom of that list, Openscad, that actually is, I was recommended that software by Dave Pickup a few years ago because, well, he likes that kind of thing. And effectively, it's a bit like LaTeX, the LaTeX approach to 3D printing, to 3D modeling. Effectively, you write the different constructs in codes, and then you see the rendering straight away. So if you don't like LaTeX, Openscad is not for you. But actually, for the vast majority of things, and to get something done really quickly, Fusion from Autodesk is very, very good. And because we are in campus, they actually offer it for free for the educational use. So you basically go there, you say you're in a university, and you got access to a 1-year license. Then the following year, you just go there again and renew the license. It's that simple. And Fusion is relatively intuitive, so that's what we're going to be using today. But I should stress out, it isn't the only software. Effectively, anything that exports a file with the STL extension, which is an extension you'll see a lot for 3D models, can work in this. So you're not limited to Fusion. You can use whatever you want. And there are some open source ones like FreeCAD, which I know Andy was using. Obviously, if you're more of a SolidWorks person, you can use SolidWorks. Right, so let's build a simple model. So based on that sketch that I was doing. So we start with this view. So I don't know if anyone wants to follow on their computers, but if not, I will just build it here. And then because this session is being recorded, you can watch it later on and follow it as I'm doing it. So the first thing is, remember that drawing that I did, not this one, the other one. No, cancel. Where is the other one? Yes, this one. So what we're going to do is we need to try and make something similar to this in a sketch, because everything starts with a sketch. So we go here, you create a sketch. We can select the plane. So let's start with this plane. And now we know what we want to do. So it's already in millimeters. So I think it was 150 wide, and then clearly probably around 100. 100 tall. Okay. it wasn't so critical, but it needed to be larger than 50, obviously. Right. So we've got the base plate. And we can probably add the screw holes because those are the two screw holes that we actually need. We can put them in the center. So it's important to know that sometimes when we are printing things, holes do shrink. So what I always do, especially with our printer. So what I always do is you measure them with a vernier, right? You measure the diameter, and then you add maybe 0.2 millimeters. I mean, it's always good to go. It's not a problem if you go smaller because you can always file them and make them a little bit bigger. The other way around is more complicated. It's like going to the hairdressers, right? You cannot restore the long hair, but you can always cut more. Okay, so let's place a screw hole here, and don't worry too much about where we're going. So I'm just going to say this is 6.2 millimeters in diameter. Now I've made one hole, but I actually want this to be fairly symmetric. So what we can do here is we can create constraints, and we can mirror this in relation to there. So for that, what I'll do is I'm going to create a line, and that line is going to be from the midsection. You see here, there's a middle line that appeared, and I create it. So this is actually not, I can make this into a construct, I think. Construction, yeah. So you see here, if I right click on the line, now it's a construction. So it's actually not part of the drawing, it's something to help us. And now what I do is I go here and I can do a symmetry. I need to first duplicate the object. Sorry, hang on. So if I select this bit and I copy paste and I shift it here, I don't care where it's going because that's going to be determined by the symmetry constraint. So I just moved it out of the way. So what I'll do is I will select that, and select that. And then, select that, and that. Then why are you not, you're refusing to do the, I think I need to select the object first and then symmetry in relation to this. There we go. So now you see this little line appeared. And if I ever decide to move one, you see they move together because they are both symmetric to the plane. And we can constrain this even more. So we can add a length constraint here. So we can have fix here to here and define a measurement. Where is it? Where is the measurement? The length measurement, linear curvature, because this is slightly different from what I remember from Autodesk. Coincident, tangent, no. Here, sketch dimension, sorry. So you click here on the center and you click there, and you see we've got here a dimension. Yes, we're just going to create a driven dimension. Now, I think we can move this. So it's fixed now. Yeah, so now I'm not allowed to move it anymore because it's stuck there. So if I want to move it again, I have to delete this. Does that make sense so far? So we made the screw holes. So I can hit finish sketch. We've got a p-dimensional thing in a 3-dimensional space. So to pan, what I do is I hold the shift key and then the middle mouse button, and that allows me to orbit. You can see that this is in 2-dimensional space. To put it in 3-dimensional space, we extrude. So if we click here, we can drag, or we can add the numbers there. So I'm going to put it as 1 centimeter tall. It's probably a little bit too much, but that's fine. So we've got the base of the plate now. We've got the first part of the sketch, if we remember from the drawing. Now we need to add this bit and this bit. So for this, for the collimator, what we'll do, we can do it again. We click here, and now we are creating a sketch not on the bottom on z equals 0. We are creating a sketch on the plane z equals 10 millimeters. So we click here, and you can see it moved it to the top. It shows here the top, so you can visualize different sides like this. So we are at the top. That's good. So now we created another rectangle, and we wanted this to be, I believe, larger than 30. So let's say 35, and then here, let's say 40. Okay. Now, this isn't very centered. So again, we can create another line and put it in the midsection as before. Create a change this to a construction. And now, because this is constrained, we can create symmetry between these two and that, and now it's nicely centered. Good. So now I think we can only move the box along this direction, which is what I expected. So we can move it all the way down here. That's fine. Okay. And that's all we needed to add in this dimension. So we hit finish sketch. So you can see we've got a little box here on top of the other box. So we now hit extrude again, and we need this to be larger than 30. So let's put it at 40. And we hit OK. And that is starting to take shape. Now we need to create a hole for the collimator to go through. So what we're going to do is we are going to shift the axis, the plane of the sketch. So instead of doing a sketch from above, we are doing a sketch from the front. So we click on this plane and we hit sketch. And as you can see, now we are perfectly facing the part. So again, what we can do is we can create a line. We can select in the middle. And that is a construct. And now we can create a circle right in the center. And we can do the 30 millimeter diameter. Now, remember what I said about the filament shrinking. So probably 30 is not the best. So let's say 32. 30.5. I would normally give it at least half a mil of diameter extra to account for the shrinkage. So we hit finish sketch. And now we need to actually take material off. It's not putting material in, it's taking material off. So we could have created a hole, actually. That would be the same thing. But we decided in this case that this could work. So extrude also works in the other direction. So if you click here and you, instead of pulling, we push it, it doesn't matter because obviously here is empty space. See, the operation changes to cut. And then you hit OK, and ta-da, we've got a nice little hole here. So that's all sorted. We've got our collimator mount. Now the last thing was the slot for the cylindrical lens, and this is where it gets interesting. So we could just go and measure the lens and think about how it's going to be, what that dimensions, the thickness, etc. Or we can be more clever and go to the Thor Labs website. So I can't remember how this lens was called, LK 8036 L2. So there we go. There's a cylindrical lens here. Doesn't matter if it's B or C. I mean, this is only the coating. And we click on it. And you've got here, obviously, you can click on the AutoCAD PDF and that will tell you all the dimensions, etc. But actually, we can do better than that, because if we want to have a bracket that is exactly the shape of the lens, they've got a SolidWorks download here. And obviously, I know that we are using Fusion, not SolidWorks, but Fusion also can import and convert from SolidWorks, and that's exactly what I did here. So you can, by hitting this upload version, because the difference with Fusion is a more consumer-oriented or end-user-oriented rather than professional-oriented software. It's got the best bits of AutoCAD, but without the complicated bits. That's why it's more intuitive and easier to use. But everything is run on the cloud, so you have to create an account, and then you've got storage. You can collaborate in projects, which is quite nice if you've got more than one person doing stuff. But it also means that any project files need to be uploaded to the cloud. So, but you can do that very easily, and it will convert SolidWorks stuff into something that can be used. So for instance, here I've got one of the big OCT lenses, the LSM02. What happened here? I need to save the design. So let's save the design. Let's call this test. Very imaginative. And then we dump this here. And ta-da! We've got the LSM02 lens, which we can move around. We can rotate it. So it's got all the details from the model with all the dimensions. So I'm going to cancel that. I'm going to take this away. So you can see it's inserted here. We can kill the visibility and that disappears, or we can just erase it completely. Okay, so based on that, so another quick little tip. If you want to pan rather than orbit, you just use the mouse middle button or the mouse wheel, and you can pan around like that. Okay, so I've got here the lens. So I'm just going to drag and drop it. And actually, this lens is a lot smaller than the rest of it. But that doesn't matter because we can scale this. I believe somewhere there is a way to scale this model. Move copy, scale, place face, scale. There we go. Entities. Why don't you scale? I'm pretty sure that this was able to scale. Maybe not. Maybe not. Okay, never mind. We'll just make a very ridiculously silly thing. But obviously, in this case, I should have used a larger cylindrical lens because the rest of the components are enormous. I mean, realistically, a collimator is not that big. Sorry? In modify. In modify? No, below. Oh. And then you have scale. Yeah, I did that. I did that, but it doesn't work on this mod on the external module. I think it's only on parts because this is a different entity. It's not. Thanks, Adrian, but no. No, thank you. Okay, so let's just move and copy, and let's just put it in front of the thing and ignore the fact that it's looking gigantic. So we can rotate, and we select. Well, we used to be able to. Why can I not move it again? Move, repeat, move, copy, rotate, components. Ah, that is it. Now, we select the axis. Yep. Now you see we can rotate it, but actually that's the wrong axis. That's not the axis I wanted. So let's do it again. Because I wanted the other axis. I want to be able to basically put the lens on its top. Components, rotate, select the axis, and we go this one. Let's zoom in a little bit. This one. And oh, I didn't select the component. Oh, I did. Why are you being silly? Sorry about that. This was not meant to be happening. Apologize for that. It's a component. It's this component. Aha, there we are. Right then. I don't know what's going on here, but the axis is wrong. But what I wanted to illustrate here, if I actually had the thing properly, is that you can actually use this and subtract one thing from the other. That is actually what I wanted to show. So by going to where was it? Sorry about that. There was a possibility to take this and cut the other one, but I cannot seem to be finding the. I think that's here. Yeah, and now if we hit extrude, what? Why did you do that? Select this face and extrude. Capture the current. Capture position. Yeah. There you go. You see, we can actually cut using the information. Well, we were, if I, what happened there? Cut. Cut. Why you mean no target body found? Ah, because I already cut it. Okay, so you see, it's already been cut. So I created a little shape for the slot. Anyway, so I apologize. It didn't go as well as I planned it, but that gives you a little idea of the kind of thing you can do to sketch it. And then obviously, once we've got the model, and this one obviously is hopeless and it's a bit rubbish, but we can get it ready to 3D print, because as I mentioned earlier, we have to export these as an STL file, which means we have to get this out of Fusion and put it elsewhere. So if we select here and we go into the Tools tab, you've got here this Make option. You can actually send this away to be printed somewhere else, but obviously we've got our own printer, so we don't need that. So you could save it as an STL file and then load it to your 3D printing software. I'm going to explain more in a bit. Or you can directly send it to the 3D printing utility. So we've got here, I've already pre-configured this for Flash Print. And Flash Print is the software that FlashForge makes to use with their 3D printers. So what I'll do is I'm just going to send this model to Flash Print. So if I select all of it, why can't I select the whole lot? Oh, now I see, because this has disappeared. Okay, so there's the cylindrical lens shaped hole, because obviously we don't want the cylindrical lens itself. We just want the hole that we created. Okay, so we select everything. That's the selection, and then we hit OK here, and that opens. Yes, put it on the platform. That opens it, and as you can see, because I've designed the thing with 15 centimeters by 10 centimeters, so I was thinking, yeah, this is in millimeters. So that's 15 centimeters by 10 centimeters. It's a huge, gigantic bracket. So that's why the lens looks so small there, because yeah, I scaled it in my head too much. So it's just about fits the plate. I mean, you could scale it if you wanted to, but obviously you scale everything together. So effectively, this is a very interactive, very easy, intuitive GUI to get the model in the printer. So this is how it's going to be printed, if you want to call it that, on the actual printer. And then we could just hit print here, and we could get it underway. Well, not so fast, because perhaps not so much in this. Well, even in this, especially if I scale it, even in this model, which is relatively simple and innocuous, you may have problems if you print it like this, because as I told you, the printer will go and will go layer by layer, and vertically. So it'll get to a point when it gets to about here and starts building this section above. You will have areas where you're going to have a bit of an overhang, and so because of that, if you don't do anything, chances are that as you're depositing this layer here, it might just fall off, because if the angle is too steep, you won't have anything to rest on. So actually, that's why I've got here the supports button. If you click on the supports button and you hit auto supports, you see that it added these little tree structures inside this void. This is very necessary, because if you don't do that, chances are that this, as it's being deposited, might just fall off, and you end up with just a spaghetti mess in the middle. So you will want to do the supports. Sometimes you are able to get away without using the supports by being more clever about how you print. So you can rotate the model, and by rotating the model, you see, now we don't actually have a problem there. We may have a problem. It's not fully rotated. That's the problem. I needed to, because that makes life even harder. You can actually rotate specific fixed amounts of 90 degrees, which is probably what you want. But even then, we've got another problem, because now you've got this overhang here. So if we create the support, it's going to have to support this structure here. It won't need to support the hole inside, because now we are depositing from the bottom up. So actually, this will become more evident if I hit the print button, because then we can evaluate how the layers are being deposited. So you see here, it created 486 layers, and we can scroll through them and see exactly how the printer is going to be printing. And as you can see, that's how the printer prints in. Okay, so from the bottom up. So there's been a few things that when I hit the print, it happened. So let me get rid of these supports. And actually, I'm going to get rid of the model altogether and just load a model that I've got here, which some of you might have seen. It's called Benchy, and that's this little boat. And this boat is used to benchmark 3D printers. So if you want to test a new brand of 3D printer, you normally print this model, and then, because it's got lots of features that 3D printers struggle with, namely, you've got this massive overhang on the bow of the boat, you've got structures inside, you've got angles everywhere. So if you're trying to print this without supports, that's going to be a mess. So you have to support. You hit the auto, and as you can see, these structures, which are sacrificial, because they won't be part of the model. You will cut them afterwards, but you have to print them like that. So, and obviously this is the preferred direction for printing. Let me get rid of these supports, and I'll show you some advanced print settings. Because as you can see, if I don't put any supports, even if I don't put any supports, there's some additional material that is printed. Namely, you've got this little base, this little pedestal almost. That is called a raft, and normally that is needed. So actually, it's on the default settings. It's printed, and effectively a raft ensures that the model stays in contact with the base on the very first few layers, because otherwise, if there are some ununiformities in height, you might not, and you start by building the model almost against the plate, you might skew the things up. So it's important to build that raft like a solid base. And again, this is sacrificial material. You peel it off, because as you can see here, Benchy does not have the raft. This background feature is making Benchy invisible, but yeah, so I've peeled off all of that after it's been printed. So you've got a lot of different parameters here, but I would just say leave it on the default settings. The temperature ones, sometimes you can tweak them a little bit, but I think at the moment that's pretty good. One thing that you might have noticed is when I print and we go layer by layer, you see that there's this sort of hexagonal structure inside. So this is what we call the infill percentage. So effectively, the printer, to save time, it won't deposit material in every single point X, Y, Z of where it's supposed to be part of the model, because otherwise it's going to take forever. It's going to use a lot of filament. So effectively, you can play with this infill here and this infill tab. You can change the different kind of patterns. So you can do line, hexagon, triangle, 3D, and you can change the density. So for instance, if I put this 60%, and then I go layer by layer, you see the hexagons have turned smaller, but the print job nearly doubled. It was 1 hour and a bit, and now it's 1 hour 46 minutes, and there's a lot more material being used just by increasing the infill from 15 to 60%. And this was printed with 15%, and it's quite solid. So again, it depends on what you are going to be doing. Sometimes it's useful to print with a larger infill, sometimes not. Sometimes you might want to print on a rapid mode, just because you I think you even have a, no, there's no, I think this is the advanced mode. Yeah, I've got this in expert mode, sorry. How do I change the settings to be not the expert mode? Basic mode. So this is probably going to be the view that you're going to be seeing, which does not have a lot, but it's got the support and the raft enabled by default. And obviously, if you print in low, it's going to be less accurate. You can see that there's more, there's fewer layers, but it prints in a lot less time. But you also see that there's a lot less vertical steps. So the printer effectively is cutting corners there, compared to, yeah. And actually, you don't save that much in filament, but you do save in time. And obviously, that is the big thing with the 3D printer is, especially if you go for a complicated or a large model, it can take, sometimes jobs can take 5 hours, 6 hours. So you have to plan those well in advance. Okay, so we built a model. We've exported it as an STL file. I've shown you how to operate the Fusion, the Flash print software. Are there any questions at this stage? We are on the 1 hour mark. So I think Adrian B will have to disappear, but I'm just going to show you how to operate the printer now. But before I do so, are there any questions at this stage?
I posted a few questions in the chat.
Okay, should I answer them? Okay, drop?
No, that's too old to answer.
Okay.
It needed the
yeah, kentac.uk. It's fine, George. I installed this on home computers.
Yeah.
And
I wonder if any of the folks who are joining us from, I think, is there anyone who doesn't have a Kent email?
To be fair,
yes,
George.
me.
Andre, maybe.
Yes, I'm actually also quite interested in the 3D printing. That's why I took part in this 3D printing workshop. And I was interested in the settings that you give to your 3D printer to have the optimum.
Yeah.
So,
there is a bit of tweaking and a bit of trial and error. To be fair, Philippe, I don't see myself as a complete expert in this. We tweak and we experiment for a lot of things.
Yeah, the same applies to me. Sometimes things work better, sometimes a bit less. But yeah, maybe you have some extra experience on this.
Yeah, one thing that I can tell you is don't cheapen out completely on the filament, because we actually had a lot of problems in the last month or so with the prints not going well, and I tweaked a lot of parameters. I did a lot of research, a lot of calibration with the printer, and it turns out it was the filament. The filament that we had purchased, which was actually from this brand, from the brand of the printer. I mean, the FlashForge is Chinese, but they used to have a better quality control than they do now, and the filament is just not consistent across its length, because you buy it in a spool. It will all become apparent when I go to the other room and show you, but effectively it comes in a spool, and it's got a certain diameter. I think it's 1.75 millimeters, this one. And the key thing is that it should remain being 1.75 millimeters over the 60 or 80 meters of it. And in this case of this filament that we bought, that was a bit of a dud, it wasn't. So I had jobs that would start very well, and then halfway through, I would end up with a spaghetti mess because certain layers didn't get deposited because the filament was actually thinner on that particular location of the spool.
Yeah, my experience was also that when you want to print an edge, that this applies a lot of stress to the material, and then if you print something above the edge and above, then you might get into this position where you just have a dislocation, and then the printer just prints into air or into nothing, and that's Did you make good experiences with first printing, or like making a speed print with less infill and then going for the actual print, or like, I don't know.
Sometimes. I mean, we do spend a little bit of time prototyping. I find now that we've got this last filament, I don't have to experiment. I'm printing on the default settings, and it prints perfectly.
Okay. Sometimes, so you have this flash print PLA.
Yes. Yeah.
Okay.
Yeah.
We have different. We have these Prusa 3D printers in Tampere, and they have the Prusa PLA. That turns out to work actually also quite fine. The only issue that I have is that if you want to have smooth interfaces, then that's also a bit of an issue by itself. Did you have similar
in general,
experience?
It's bad. Yeah.
Yeah. So, did you try to polish it afterwards?
Or? Yeah, and there's a product that I bought. I haven't actually experimented with it yet, but effectively it reacts with the PLA and smooths it and applies a resin. So this is when I mentioned earlier that you can paint these. This is actually for the community of modelers, people that do things like figurines of action heroes and things like that. They print a lot of these models, and then they paint them, obviously, because that's what they do. And in that respect, they seal the PLA printed parts with this resin, which also fills in the gaps and creates a sort of a smoother cover. I mean, I find that for what we do, we don't need that. The reason why
sometimes you might need it, but okay, interesting.
So there are some. So I mean, we're only really. I've only really scratched the surface here, because there's a lot of things you can do with 3D printers, and a lot of and I don't yeah, I don't want to fool anyone. I'm not a full-on expert on this. I am just a user who happens to build some stuff here. So it is a work in progress. So a lot of this is
for designing adapter plates, like in the way you did, it's the perfect tool in my opinion, because you can just easily print it and you have the piece within 1 hour. Whereas if you would design it and give it to the workshop, you would first have to do a drawing, then you would have to explain the drawing to the workshop guys, maybe do some small modifications to it, and then maybe if you're lucky, you get it in 2 to 3 weeks.
Exactly. So, exactly. Exactly. Absolutely. Absolutely. So effectively, because we don't do that, it's a lot quicker.
Especially for adapter plate designs, this really makes the work for researchers like in the applied field a lot faster. That's a very convenient tool and very powerful. So I really, I'm really looking forward to what will come next with this.
Yep. Okay. Yeah. So I'm just going to show you how the printer works. But before that, so one thing I did not mention is if your model is too complicated or too big, and I've got an example here. I've made this imaging trough in the past. So this is already split. Let me see if I can find the actual original version that wasn't split. So just bear with me for a second.
Manuel, you also wanted a question.
Yes, go ahead.
Questions, and I had one. You know that when people create software, and in 2 or 3 years' time, we give the new people arriving, students or PDRAs, the previously created software, there is always a problem. Each one would prefer to do their own software again and again.
Yeah.
With these designs, is there any way in which when you create a design, someone who comes as fresh can take that design and develop it more, or it would be difficult for the newcomer to take it and continue?
It depends. It depends on what software. So obviously the STL can still be imported and you can still do things to it, but you won't have access to the sketches per se. So the bits that I did here, if you would export this as an STL, you could scale it, or you could print it again, or you could integrate it into a different design, which would then you'd be able to take material off it or add stuff on top. But you wouldn't be able to say, okay, I want to add a sketch here on this plane or here on this plane, or adjust the diameter of this.
Exactly. So what you have to do is all this. If you wanted that not to be for you only, to be in time to have a database of designs, or
I mean, ultimately,
people can continue.
If people use the same software, they can share it around. This is, I guess, basically goes on George's point that we can have the designs available on a central group repository for people to use. So actually, I created an AOG team on the Fusion thing. So if people want to join, they can have their shared things. So if they've got specific mounts, specific adapters, things that they want. So for instance, I've got here some mirror mounts, some phantoms as well. You know, print things that we've printed in the past. Spacers. So for instance, this is a spacer for a Thorlabs lens to create a gap between the lens and the surface that we are imaging. So if people are members of this team, they can have access to these projects. I can share that with them.
One other thing and consideration is that even if we don't have the 3D printing in mind, it may be helpful to design things in AutoCAD to have them made in the workshop.
Yeah, because we've got access to the Fusion 360 education, we can actually create the technical drawings from here. So that is possible to do. So if you can.
And actually, I mean, in terms of, for example, the NetLAS, students, it is another skill, isn't it? It's something else you can say that you're sort of picking up as you do your PhD, be able to put on your CV. I mean, it is completely optional, of course, but having the opportunity to learn that is valuable.
Yeah. So yeah, so you can make the technical the drawings like this. Yeah. So the kind of technical drawings that you would use then to take to the workshop. So that is also possible to be done with this. And then you can export them as PDFs. So effectively, you can do that as well. Okay, I'm just going to show you one example here. So obviously, you've got here this big thing. Let me see if I can open it on. Come on, Windows. If I open it with 3D Viewer, yeah. So the STL files will open in Windows 10 as 3D objects, so you can pan around and watch them. So this one was something I've made for my incubator probe, because for those who don't know, I'm building a system that needs to be placed inside of an environmental chamber and be left alone. And I've created a box that is insulated, but I have to place a sample and image it from below. And obviously, to make the interface and to where I'm mounting the sample and with the lenses below it, I 3D printed something. So I've got some screw holes which bolt to the top of the lid of the box. And then I've got here space to put a glass window, and then the lens is underneath. This is actually a very complicated thing to print. And actually, in this case, I was advised by Phil March to split it, because the problem is, so if I load this into you'll see the problem. So if I load this into Flash Print, if I print it like this, it's going to require a lot of support on this side. Yeah, exactly, Julian. Exactly. So I don't know if you guys are seeing the messages on the chat, but yeah, Julian said you can modify someone else's model. You can add stuff to it. You can add material, extrude, but you won't have access to the intermediate steps. It's like for instance, with perhaps this is a bad example, but because some of you might not use it, but with LaTeX, if you've got the access to the source code, you can modify everything. If you only got access to the PDF, you can open the PDF in Word and kind of do some botched up modifications, but it's not going to be, you're not going to be able to recreate, say, the references and all these things, because you don't have access to the source code.
So yeah, I wanted to add, even if you have the source code precisely, there's only so many things you can do, because by trying to modify an intermediate steps, you're going to destroy the following steps, or make them impossible to.
Yeah, and it also depends on how people have built it. I mean, if they've built it with conditions and constraints, if you modify something, the size of something, it might propagate and it might do all right. But if you just put a hole there, it isn't. Yeah. It depends on how disciplined the original person was at drawing it. But I find that actually for the vast majority of things, you can probably sketch it yourself, and you're going to be working perhaps more on your own in these things, because ultimately you just want to print a little bracket or a little something to help you get going.
Very specific to your application, usually.
Yep. Although, as George said, I mean, if there's something complex, perhaps we should document it and keep it in a centralized location so people could reuse it. But then that is assuming that people are going to be using the same kind of software to open it. Okay, so now going back to this. So as you can see, in this orientation, it's terrible. I mean, if I hit the supports button, it created this plethora of supports. It's not the preferred orientation whatsoever. So we're going to clear the supports, go back, and we rotate it, and then we move it to center it on the platform. Okay, so this is probably the best way, but the issue still is we are going to be creating the support structures on the inside. And the issue here is we're going to need to remove these sacrificial structures here. But this surface, I want it to be nice and smooth. It should be nice and smooth because it's where the imaging dish is going to be resting. I mean, I could always file it, but it's not great. It's not the best idea to have something a little bit rough here. So actually, what I'll do is I'm going to delete the supports, go back, and instead, what I'll do is I'm going to cut this into two pieces. So how do I do that? So we go here, and we do plane Z. We move it, and we cut. And now, take this and we put this out. So actually, you can print this one first and then print the second one. So you have to remove this bit. But in this way, when you're supporting it, sorry, this is going to be a lot easier to print than the thing combined. And that's exactly what. And then you can glue them later. You can use hot glue. You can use cyanoacrylate, i.e., super glue, and you can place the things in place. Or if you want to do it even with no gaps, you can dig out the old soldering iron, and after you've glued it, you can smooth the edges with a soldering iron, because that's just going to fuse the edges and smooth them together. Because again, PLA fuses at 210. Okay, right. We've seen all of these. So if I wanted to say to print this, so I'm going to cut this bit. Yeah, so now it's okay. And now if so actually I could put supports. Actually, he wants supports for this overhang here. Okay, so we'll leave out because yeah, there's a slight gap here. We print it, and I'm just going to print on default settings, and we've got a raft, we've got supports, so we hit OK. And you see here on the top, it tells me how long it's going to take and how much material it's going to use. Now, if the printer was properly networked, which it isn't, you could actually send the G code straight to the printer and print it directly. At the moment, what we do is we simply save the machine code, which is this extension .gx, and we save it, and then we simply dump this in a flash drive and take it with us to the 3D printer. So that's what I'm going to do now. So I'm going to switch to my tablet, so I can go with you. I can take you with me to the 3D printer. Just bear with me for a second. Just joining Teams on my other device. Come on, Teams. Yep, join to share content. Add to this device. Okay.
Is that sufficient to drink a sip of coffee to be switched to another device?
Okay.
Can you hear me?
Yes,
Yes, we can still hear you, but
you still have your screen sharing on.
Yeah, that's fine. That's fine. I'm gonna turn the camera on in a minute.
Ah, okay.
So camera on. Okay, can you see me?
Yes.
Yes, we can.
Okay, good. So I'm gonna switch the cameras around. Okay, so that's the 3D printer right here. Perhaps it will be good if I unpresent the other computer, so you can. So my video is actually big in the recording. I'll be right back. Okay, right. So switching the printer on. So that's the printer powering up. So obviously now this session is very specific to this printer, but most FDMs work in similar ways. It's got some nice funky beeps.
Our printers don't think that's already a difference.
So this is where the filament lives. So we spool it this way. Perhaps at some point we can have a proper. That would probably not be that useful for Felipe and for the other NetLab students that aren't actually here. But I'll show people how to load and load filament and all that, those little things that are specific to this printer. But effectively, to print, all you do is, as I said before, you've got the flash drive. Where's the camera? The flash drive, which I've preloaded the file. Make sure we've got filament, which we do, and then we just plug it in. And this camera has some interesting features which we haven't fully explored. Namely, it's got a camera, so you could monitor the status of the print remotely. It's a bit hit and miss because sometimes the web interface works, sometimes it doesn't. So it's not something I would recommend using too much. So this is how the user interface looks like. So we can just simply go on the directory, look for a file, say, let's print this little thing here, because that's going to take only 16 minutes. So simply, this is something I already had loaded in the file in the flash drive, and all you do is you press print, and that should just print with the raft, with everything. Let me see if I can find something simpler and quicker. What is this test rod? That's longer. As you can see, I've got plenty of things in my thumb drive. I'm just going to print something really simple just to show you exactly what the printer is doing. So let's try this one. So as you can see, if you look here in the control panel, the printer heats up the extruder head. So that's this here is the extruder, and this here is the heat plate, the base. So the base will heat up to about 50 degrees, and the extruder will go up to 210. So it's already begun heating up, and it's starting to reset to get the positioning between them.
Manuel, can you show again extruder, because you said here, yeah. And I don't think I could follow.
So the display will show you on the left, it shows the temperature of the extruder, and on the right, it shows the temperature of the base plate. Good. So on the left, it's currently starting to heat up, Yeah, it's going okay. 47, 53. So now it's starting to heat up the actual extruder, because the base plate has already hit the actual temperature, which is 50. And as you can see, the extruder is right over here. It's got a little bit of filament stuck to it, but currently it feels very, very solid because it still hasn't achieved the temperature. It's still on 170. But it's about to start. It's heating 200 degrees, 205, 206. So it's 210. So as you can see, it began, and it will start by doing the raft. So as you can see, it's printing the raft first. So this is the base of that little ring. Let me get a bit closer.
So these devices can control positions to within a couple of tenths of microns without OCT?
A few microns. It's a stepper motor. I think it's 10 microns, the step size of the vertical. It's all mechanical. As far as I'm aware, there's no optical positioner here.
Manuel, can I give you a slight comment about this thing, like that this extra PLA is hanging down in the very, very start? This always happens also to our printers, but then what I do is, before I start the printing, I basically click, there is some option that you can say choose or like load a new PLA or like a new filament. And then it kind of first just prints into the air, like just like a string of PLA, and then you can just pull that out so that the nozzle is really completely clean. Because I mean, now you are lucky because it's really not in the way of where it's 3D printing the part. But this might actually happen at some point, and that might.
No, that's a good point, and we can heat up. We can preheat the extruder to the fusion temperature, pull anything out. But actually, the way that 3D printer works, because we always print the raft, that's never going to get in the way.
Okay.
It might be an issue with some 3D printers, but in this one, very rarely I've had problems of that nature, simply because the printer always prints the raft first.
I see. Okay.
The bits that it's currently printing, none of this is actually part of the actual model. This is simply the base for the raft.
Okay, I see.
So it's still doing the base.
And does it always have the same settings, like what's the PLA flow and so on, like these?
Yeah, this is on the default settings. I mean, as I said, you can probably get a little bit more technical, a little bit more advanced, and do some tweaks. But I found that the biggest problem was the quality of the filament, rather than the printer prints very, very nicely on default settings. What can happen sometimes is it might fail to adhere to the base, and so you might need to perform what they call a Z calibration. That is just to tell the printer where the zero of the Z stage is. If you find it too low, then the nozzle will ram into the plate, and if you're too high up, it might just deposit it in midair. But depositing it in midair, because we do the raft, the raft is a much coarser position. So even if it's deposited in midair, we're only looking for the zero of the Z, I believe. So anything above it, it's going to be stepped, because the the Z is working on a steppered stage. So
yeah,
still,
that makes sense. Yeah,
it's still doing
thanks a lot.
the raft, as you can see. So the raft takes a bit of time, depending on the complexity and how we slice the model. It might use a bigger or a smaller raft.
And what's a typical infill of the material that you use?
The default settings here is 15%, and we just
Only
use
15. Okay.
15, 1.5.
Oh, okay. And that still holds your optics and everything.
Yeah, yeah. No problems whatsoever. Because we do the hexagonal shape, which seems to be the strongest one.
Yeah.
But obviously, the infill only applies if the structure is thick enough to warrant having the hexagonal structure inside. Because if it's a very thin thing, then you just have 2 layers.
Yeah, exactly. When it's only 15%, then yeah.
But yeah, in terms of it's obviously not very dense, but that's fine. I mean, for the payloads that we are talking about here, it's more than enough. So yeah, obviously the big thing here is, and this is again for the AOG users, you have to check how much filament you've got before you start the job. Because obviously you don't want to run out of filament midway through a 5-hour or a 6-hour job. So you need to make sure you've got enough filament on the spool, and should log it on our shared equipment log file that is on Teams, because we buy it centrally, so it's bought from research grants and projects, etc. Just to keep track of how many meters people have used. You take a note of how much the machine is telling you that it's going to be taking, and you add that to the list, just so we know how much. Okay, so as you can see here, it's already started to build the infill. Let me get it closer. You can probably see, if I turn off the light, it might be easier. Hang on. So as you can see, it started doing the infill. Then you just wait. You can see here how much time it's got remaining and all that. So it's pretty simple. It's pretty straightforward. You can check additional details. You can see how the temperature is currently doing, how much filament it needs to use, what's the progression on the job, and all that. This can also be viewed remotely if you've got the flash cloud thing, which doesn't work very well. I've used it before, and it occasionally works and occasionally it doesn't. So I wouldn't bother too much with it. And either way, we've got a firm rule that someone needs to be in the building when the 3D printer is being used, because we're using 200 degrees here. I mean, if something gets jammed and locked and the printer doesn't turn off, there is a real possibility that it could catch fire. So because of that, our rule of thumb is we don't leave the printer running if there isn't anyone in the building to turn it off. But that's it. Okay, I'm going to go back to my station. I'm going to stop this because I don't think there's any point in continuing this. And then we can answer some questions. Let me go back to my office. Okay, right. So are there any questions?
What would you estimate the time to learn to use the system was for you? I mean, I guess you may have also come into it with some knowledge. So
yes. So I mean, in my case, my trajectory was a little bit different because during my undergrad, I actually had a workshops module, so I was already familiar with CAD software to an extent. Yeah, it's a difficult thing to put time on, because obviously I would imagine that the first job I did, it took a bit longer, and it depends again on how complicated the model is and how much trial and error you have to do, because sometimes you model it, you think this is going to work, you print the part, and then you realize that actually is not, or that you forgot something, or that it doesn't quite fit, and then you have to tweak it. Sometimes you can tweak it without having to reprint it. Sometimes you actually have to go on and lose another 5 hours printing. So you try to avoid that as much as possible, because that is the real time here, is waiting for the printer. And then luckily, because not a lot of people have been using it, that means I can actually afford to wait 5 hours and not be in the way of anyone. But I think, yeah, the job, the time on the job is important.
Yeah. My question is, I mean, it's obviously infinitely customizable, well, almost, but so that's a huge part of the attraction of going down this route. You can make anything, and the most bespoke part, you can make it.
Yeah.
But then, I don't know, if you've got to, I guess you need to see some return on your time investment. If you're only going to make the 1 or 2 bespoke parts during your PhD, yeah.
But then, I mean, for making simple things, Fusion is pretty intuitive to use.
Yeah.
And actually, it's not just for 3D printing. You can use it for making technical drawings, for taking things to the workshop as well.
Yeah.
And I'm not entirely sure, but I think you can also use it to do what Alejandro is going to be telling us about with his 3D modeling software.
Right.
So to make diagrams for your to illustrate your papers, etc. Which again could be perceived as a little bit of a gimmick, but actually sometimes if you have a system that is inherently 3-dimensional and you want to illustrate that is 3-dimensional, it's quite nice to be able to have a render and have a few views. It looks nicer, but it generally can help visualize it. So it's not completely just for 3D printing, but I just found that for a lot of things, for instance, this thing with the cylindrical lens, which I failed spectacularly during this demonstration, but I've done this before. I just physically could not get a Thor Labs part for that size, because I needed to mount both the collimator and the lens to a translation stage, and they needed to be. I didn't have a lot of room, and I needed it to be within a few millimeters together. So printing something like this allowed me to just say, okay, fine, just insert the lens, put the collimator in, and that's it. So that is where I see it being useful, and I think it will be useful for anyone that needs something that they cannot get from Thor Labs. Obviously, that should be the first port of call is, oh, can I just attach this to a breadboard and get a mount, because they would necessarily be more solid, etc. But sometimes you may not be able to use that, and that's where this comes in. But to make small things like say a converter, you've got a 1-inch lens mount, and you've got a lens that is of a weird diameter, and you want to put it there. You can very, very easily make a cylinder with the hole that has the diameter of that lens and the outer diameter of that 1-inch mount. You know, it's effectively 2 circles, and then extrude for a few millimeters, and you print it, and you're done. So things that simple, but it saves you having to go and pester Ian, put a cost code, wait for a few weeks because he's always incredibly busy. Where you can do the 3D printer can print that in 10 minutes, and you're done.
Yeah, we have exactly the same issue here. So the 3D printer just saves a lot of time in that sense. And just getting started with a 3D printer from scratch is actually quite easy. There are a lot of custom-made models from Thingiverse that you can download, such as this jolly boat that Manuel also presented. And then when you speak about the design, you would have to do that anyways, even if you would consider the regular workshop. So really, like, the only win that you get out of it is the time that you save by not having to use the workshop so often. And it also saves them a lot of time.
Yeah, and cost, because over here it's costed, you know, and I think I remember the nominal figure was about £60 an hour for workshop time. So it is, and obviously that's billed to the project, but yeah, it is a bit of money compared to a roll of filament is half of that, and you can print a lot of things with a roll of filament.
Especially with your 15% infill.
Yeah.
Okay, thank you very much, Manuel. Sorry, I have to get going, but thank you for this workshop. It was really helpful.
I hope this was useful. If anyone has any questions, obviously feel free to drop me a message. My email is on the AOG website. If you got any issues, yeah.
Yes, Philip is scheduled to visit us.
Yes, hope to see you soon. I am working as hard as I can to make this possible as soon as I can. But yeah, it still takes some time, but things are going on. Looking forward to seeing you all.
Yeah, looking forward to seeing you, Philip.
Have a nice weekend.
You too.
Bye.